All right, y'all, what's good? Before I start, I just want to say Discord's up. I'm gonna put the link in the description, and then for everybody who's asking, you know, feel free to join, ask whatever questions you had or whatever. But yeah, we're gonna be up in there, and now we continue. So where I'm at right now is, oops, is um I need to test because yesterday when I left off, I don't think I tested anything. Uh, so let's see where we're at. Actually, you know what? All right, so I can open all of the tests in here, and then test. Oh wait, sorry. This is hash table, and then test, and then everything in there. So this one was adapted, right? Yeah. So let's make this over here. Oops. There we go. Project. Build. Oh shit, I did that wrong. There we go. What are we doing? What are we doing? Hash table. And then let's run it from here. So we have source, hash table, and then we also need boarding pass example, and then we need test, add test with the double alt tag. And let's run it. So what we're expecting here is we should have two wills, both with different places, and then a not will. So will, not will, and will. And it's 1, 2, 3. Okay, cool. So that works. Oh, actually, let's do an empty test here. No, wait, we know it's working because all the other stuff is null, so we're cooling. Yeah. So now what we need to do is create boarding passes for all of this. Let's just say B1, and then we have, oh, I forgot what it was, create boarding pass, and this will be a random integer with like 1,000 or something, and then its first name, B1 first, and then B2, or no, B1 last, right? And then we need to do this 1, 2, 3, 4, 5 more times. Wait, 1, 2, it's 5 total. 1, 2, 3, 4. So 2, 3, 4, and then 5. Is it G? Yeah. I'm a fucking genius. B1, B3, G. B1, B4, G. B1, B5, G. Okay. And then this is gonna be B1. Let's actually name these. Key 2. key 4, oops, B4, and this is key 5, B5, right? And then find value. Oh yeah. Test is the table. So and then let's do an edge case of something that isn't in it. And then we'll just go sequentially so it's easier. Key 1, key 2. Oh, it doesn't go backwards? Shoot. Interesting. It does go backwards, but not here. And then, huh. Key 3, key 4, key 5. Key 4, key 5, and then something that doesn't exist. Okay, so what we're gonna do is we're gonna do one part at a time. So I'm pretty sure this works, but just in case. Oh wait, I'm on find test. Oh, is it? It's a standard live, right? Oh wait, Rand doesn't show up, it shows up as something else. I'm gonna assume it's standard live. Oh, where's my completion for that? Oh, my completions are off in general, what the fuck? I'll figure it out later. And my highlighting is off, that's very odd. So we have, at this point we should have B1, B2. Why are these all 0? Am I misunderstanding what Rand does? No, I'm not. Oops, a little too far. Okay, why isn't this working? It's very odd. Was it the same last time? Oh, they were all 0. Okay. So how do we generate? I don't know why this is here. Oh, I never said it. Duh. Output. Oops. That's not what I meant to do. Output. ID num is ID. Simple as that. Oops. Well, that's but it works. Okay, so let's go back to find test. So we should have, all of them should have different values. And we have keep 1 through 5. So 383. Oh, all of them are right next to each other though. Which shouldn't be the case. I think they should be separate. But all over here with different IDs. Okay. Oh, shoot. That's why they use a different one, because these are going to be right next to each other. Okay, what's a different algorithm I could use? We can just think about it. What if I just multiply this by a constant? So, so what if we say constant multiplier equals, you only need the equals, bam. Wait, that was a bad number. It's something random, right? And then we can say okay, so it's constant multiplier times key value and then the modulo of that. Let's try that out. Bam. Bam, 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 bam. So all of them are different numbers, right? Yeah. And we have 1, 2, 3, 4, and 5. Okay. Awesome. All right, so that's that one. And then we can come down here and do the finds. Format int, but is type. Oh, shoot. These should be. Oops. Damn it. S, D, S, enter. Okay. So this should be boarding pass to string. Actually, ooh, good idea. Undo that, and then we just come through here. We say S, find value HT, and then we do boarding pass to string, find value HT, And then that. Right? Oh, I'm still missing one. There's a lot of parentheses. Is that right? Oh, I have an extra one in here. That's... yeah, it is an extra one. Right, and then you have 1, 2, cool. Okay, so now we should be able to do it. Oh, actually, let me not print here. These already have printfs, so I'm gonna put that in the... Oops. Oh, actually, I did need that. Reason being is I need to verify that everything is the same. So, 383 B1, okay. 886 B2, 777 B3, 915 B4, 793 B5. And then, awesome. Last one is null too. We handled that too. Awesome. Okay. So let's remove the elements and then print it. And this should print just a full thing with all nulls. Cool. Slight. Actually, how do I do that? Let me make sure that's right. Remove. Oh. Let's free it first. Wait, why am I doing this? Just bam. And then put the semicolon here. Delete. Oh, delete till the end of the line. Awesome. Bam, same thing, but I think we're freeing some memory. It probably won't matter, but who knows? And then all of these should return null. Ooh. Oh. I need to do the same thing I did before. Yeah, just do this. Oh wait, extra one. Bam, all new, awesome. All right, so we're cooling on that one. Okay, wait, before I forget. Yeah, alright, sis. Oh. Pass me the rock. I go crazy about it. Put header guards. And then this is touching the hash function. I don't need to put like this. Yeah, we pretty much tested it in the other one, so I don't think we need to go back in that. And this was just this one. We basically did all of this in the find. Okay, so what we're gonna do now. Shout out the person. I forgot your name, but shout out to the person who taught me about Pragma once. I was doing the threes every time. It was annoying. So we're gonna go. Why did I see out of this? All right. So they said it was Pragma once, and that's all I need. That is so crazy. Pragma once. Bam. Okay, awesome. Actually, let me make sure it's on all of them. Dynamic array. Include all those. Yeah, there it is. Yeah, I was doing that. But now I don't need these. Oh, I was about to write it again. That was crazy. Oh yeah. That's a temp file. Okay, I renamed this too. Awesome. So now we have what? A pretty much fully fledged hash table. Let me make sure. Oh, I'm missing something. So header guards, bam. So we'll figure out if there's a way later on to void pointer. I don't think I need this. This doesn't seem very viable as hash tables seem to me to be specified by way of its data. But if I wanted to, could create a struct that holds primitives easily by using a union and then enum specifying type. That shouldn't be that long, but I'm gonna leave it. This is the same thing as what I just said. All right. Oh, wait. I'm not done with this. Because what you need is to handle collisions. Okay, give me a second. I'm gonna go back to a comment from Witchy, because I don't remember the name of the collision thing they were talking about, but I want to look that up. Okay, here we are. They mentioned probing and separate chaining, so I think that's in here. No, other one. Probing, there it is. Suppose we try to insert. Oh wait, it does have chaining in here too. Separate. Oh yeah, it does. Chaining. Okay. So let's read up on this real quick so I can choose which one to use, starting with probing. Oops. Go back up. Am I bugging? Okay, that's chaining. Oh my gosh, there's a lot. Let us begin by specifying our... Wait, we have two options to do this problem. First, this is the override thing. Use a different hash function. There may be, to avoid these collisions, some algorithms can calculate such a function, but they require knowledge of all the keys that will be used. So this is a difficult option most of the time. The second alternative would be to introduce some policy for dealing with these collisions. In this chapter, take a second approach and introduce a strategy known. Okay, so what we're gonna do first of all, let's update our to-do. So we're gonna handle collisions and then handle rehashing as two separate things. So this is for when two keys get the same hash, and then, oops, that's not what I meant to do. And then this is for when the table is too small for the next element. Simple, right? So, knowledge of all the keys being used. So this is a difficult option most of the time. The second alternative would be to introduce some policy for dealing with these collisions. In this chapter, probing tries to find the correct key by probing or checking. Okay, this might be silly, but I don't know what probing means in this context. Okay, so I'm just gonna say a synonym for that is checking. Oh, it says that we're checking right there. Other positions relative to the initial hash address that resulted in the collision. Let's explore this idea with a more detailed example and implementation. So let us begin by specifying our hash table data structure. This class will need view class functions to give our hash table some data. Our table will need an array of student records and size variable. We'll use an add function, set index, table of student. So they hold a key relative to each one within the class. Where's the student class? Oh, they don't show. Okay. I'll figure out the holding of that later. So that the add function belongs to the hash table class, meaning that the table and size are both accessible without passing them into the function. Once a student is added, the hash table could find. So use a search function. This approach could work, assuming that our hash was perfect. This is usually not the case though. Extend for collisions. So suppose we try to insert a student marked as A into the database and find that the student's hash position has already been occupied. In this example, student A is hashed to position 2, but we have a collision. With probing, we could try the next position in the probe sequence. So you just check the next one and see if it's updated, then do that one. Linear probing. Okay, so that's called linear probing. And probe sequence is just the order of the array, I assume. This figure shows that first we get a collision when trying to insert. We probe the next position of the array. This open addressing with probing means that collisions can start to cause a lot of problems. The functionality of collision will quickly lead to poor performance. We'll revisit this soon. As we discuss time complexity for now, we have a few other problems with this approach. Yeah, you would need to store all the keys because they're not directly linked to the hash anymore, right? How can we implement our approach sequence? Hash function to return the proper hash the first time is used. If we have a collision, our hash needs to return the original value plus 1. If we have 2 collisions, need the original value. Key and collisions. Oh, okay. Before I read the rest of this, what I'm assuming is that collisions here is an array that is the size of the table, and then that just holds indexes in which there is a collision. So like say we just do zeros and ones in that array, right? If I get a hash that's like 4 or let's use a different value, that's like 15, right? And then I say, okay, collision's 15. If that's a 0, then we're good. If there's a 1, then we need to use a different one. That's what I'm assuming, but I feel like that makes sense. Oh yeah, and also the thing about that is you can check, is the length of collisions equal to the length of the table? If it is, then you need to rehash. We get an initial collision followed by a second collision with student A that was just asserted. If the space in the array is already occupied, there's a variety of approaches to solving this problem. Take the simple approach and use a secondary array of status values. There we go. This array will be used to mark the table spaces occupied which are available. We will add an integer called status to our data structure. This approach will okay. So oh my gosh, this is exactly what I said. 0 to an empty slot and 1 to an occupied slot. Now check the spaces open. I wonder if you can make an array of bools. I've actually never done that before. The code could, well, yeah, those are just 0 to 1, so I guess so. Correct our add function. So set collisions to 0. While status index equals 1 and collisions. Oh, I see. They just went through the whole thing. I guess, yeah, you'd probably have to do that for the array. But you could, no, you can't do that. Never mind. Okay, so what's the other one? This performance is O of n, right? Because you would maximum have to go through the whole entire array. Yeah, O of n. Okay. What was the other one they said? Separate chaining. Okay, wait, let me read about this one first. What's her quadratic approach? It's approach sequence that increases by the square the number of collisions. Interesting. So it's just a way of not going right next to it. I don't quite see why that would be better. In this section, we'll look at an implementation of the hash collision factor. Approaches the ideal strategy for an open addressing. Double hashing. Strategy to open addressing is that? Oh, it's an entirely different thing. Okay. Separate linked lists to handle collisions. The nodes in the linked list are said to be chained together, linked in a chain. Our records are then organized to keep on separate chains. This is rather than worrying about probing sequences, chaining will just keep a list of all records that collided at a hash index. But can't you do that with probing too? Composition. Composition allows data structures to be combined in powerful ways. How does it work? Well, data structures hold data, right? What if that data was another data structure? The beauty is that both adding and removing records is extremely easy. Give example implementations. We will use the same student class.
Yo, this is J11.
That ended quickly. Oh, I've been listening an hour already. That's nuts. Anyway. Okay, you know what? Let's keep it simple for now. And we're gonna do let's just do linear probing. Keep it simple. Okay. So what we can do is come here. What happens when you hit the end of where's linear probing? While status is not one value. If status indexing. Why doesn't this handle the end? While status index equals 1 and collisions is less than size, set collisions to collisions plus 1, set index to hash.
A little thing we love about Chick-fil-A chicken strips are how satisfying they are. The chicken strips are amazing. They're always filling, tender and juicy. Definitely one of my favorite things on the menu.
My favorite thing is the last bite. The last bite is nice and juicy, and it's wrapped up in some crispy breading that keeps it nice and tasty. And being able to scoop
Oh, the hash function changed.
sauce with it, it's just like the best part. It's an undefeated
Set initial index to key mod size. Set index to set initial index to key mod size. Set index to initial index plus collisions. Oh, I see. Because if you hash just the key, you get the same thing every time. So that's this first part. And then if you have 0 collisions, then it's just going to return the no. Okay, I see. So for our hash, let's just say int hash equals v in parentheses. Oh, v in parentheses. We're gonna delete that. Right. And then we're gonna say we need to take in collision, or no, int the number of collisions, and then return hash plus the number of collisions. Okay, so now this needs to have, shoot, I gotta change all these. They handle collisions inside of add. Yes, so all of these need to have, okay, so add so we can say while, okay, let's say so we can say, let's, okay, while, table, passes, while table passes at the index of hash key num collisions equals, or does not equal null, meaning that it has something in it, then we increment the number of collisions and then try it again. It's hash key. Then we say if whoops. Wait, what did I just do? If the number of collisions equals this has to be a int, because this is going to change. This is not going to change. Oh, does that say fix available? It has a code. It does have code actions. So if num collisions equals max size, then let me break this. Hit end of table. Change position. Okay. So that's that. And then this will be a rehash basically later, but actually we basically just copy that. Okay, what you screaming at me for, Cling? I did forget that. That is on me. If not full. What do you mean? Not full's right here. Oh. I think that's it. Then let's make this like dumb small. Like 2 elements large. Alright, let's try this stuff again. There we go. I don't remember what font this is. Okay, wait. Why is that number so large? That has to be a segfault or something. But B3 is normal. We skipped over B2 somehow. What? Okay, let me step through this. Okay. Oh, I think I see. I never handled wrapping. Where is... So... Because if we get 2... How big is this array? What's the hash constant used for again? So if you have 3, if you have 1, 2, 3, 3 will be 0, 1, and then 2. So this does need to match, I think. I still need to wrap, but... Okay, there we go. But the problem of wrapping still holds. Because, oh shoot, if we have... Yeah, we need to check throughout the whole thing if all of them are null or not. And if we start at 2, then we're missing 0 and 1. So it needs to be... It needs to be... So how do you... Let's think about this, right? How do you wrap? Wrapping would be you get to the end and then start at 0 with your current offsets. So how do you do that? Okay. So we say if hash plus number of collisions okay, final stretch. So we have, what was I doing?
Look, I'm just saying, you could be a little bit less excited every time your entire team dies. You're the only one who's been. Just saying. Like,
I lost where I was.
dang, your gun's really good. I'm bringing it to next raid. Like, thanks. Appreciate it. Like,
Okay. So if we have, if this is
I didn't realize I had a bunker mission, actually.
equal to,
Yeah, the bunker mission.
no wait, if this is going to be greater than max size, then return the number of collisions. Wait, did we check if it's larger? Ah, first we need to say if the number of collisions. Wait, do we do that down here? Yes, we do that down there. So we don't need to do that. We just return the number of collisions. Wait. This will be minus. Oh, smart. Minus the hash. Minus the difference between the max size and the hash, because that will give us how many number of collisions we used to get to the end. And then else we do the normal. Okay. We got 3 of them in there. And then wait, what? We got 1, 2, and then 3. 4. We hit the end. Okay, wait. I think I'll be less confused if we did this. Okay, so we hit the end of the table twice, and then we printed it. Okay. Oh, why is it 5? That shouldn't be 5. So we hit the end of the table here and here, and then we print it here. Yeah, and we replaced it for some reason, because this one has 5 in it, right? Yeah. So what allows us to replace it? Actually, you know what? Let's just do GDB a.out, and then we're gonna break it at 18. Wait, no. We're gonna break at 17. So the original hash is 2. Okay. Okay, so that's correct. Now, this is the point where we wrap. Oh, did I do the qualifier wrong? Forgot it here. Wait, no. Yes. Okay, let's try that again. Okay, cool. So that is now working.
If I don't lift this one, I feel like I might need to get this. I don't think I'll be able to make it on season 2.
That ain't right.
Alright, I think I'm...
Oh, I see. We need to do the same thing. Oh, yeah. So we first check. No. We need to hold the key. Yeah, for verification purposes, we need to hold the key. And this will help for in future, because we need to do this in the future anyway to be able to rehash. So we can say hash table Oh wait, this is keys. Okay. Why do I keep doing that? I really don't need to type this up. Oops. This either. Oops. Let me double check that's everything. Okay. I think we're good. Fuck. uh, oh, I never mallocked it. Oops. I think that's it. Boom. It's not showing their keys though. Because it's not supposed to. It's only supposed to when I print, and I haven't printed. Okay, so we're successfully keeping the stuff, but it didn't remove anything. break at 26. But all of these should be not null.
Do everything have like more or is it just like the tags that are different?
Table, passes, hash key. That is not null. Am I bugging? Why is that? Dude, I'm silly. This is equals null. It's gonna work now. Invalid pointer. Oh, that means it worked. Because I try to access keys here. Oops. Let's just make something real simple. Or just say, just so I don't have to handle this. And offset. No, that should be null. Okay, where do I get that? Yeah, so GDB. What can you tell me about that? Was it imprint? I assume it's imprint. Oh, it's before that. Before that? Okay. Wait, actually, Run it again. Is it this one I'm feeling? Yes, okay. Oh. Okay. So we can access the actual table itself. So it's trying to access 0. I don't see what the problem is. Oh, when we added it, did we not malloc it first? Yeah. So first let's malloc it so that we can free it. We should be mallocing that too. I don't know why that didn't throw error. Time string length of key. Oh, we already have string h. Awesome. Same thing. Okay, you can.
I'm not the biggest fan of being there because it's like your only way out are basically in the same timeline. Are you like all the way up on like the rooftop?
Interesting. Mun map chunk. Let's see if I remember this. Fcinit address. Oh, it tells me. Awesome. What did I spell wrong? Oh. What did we try to write? Did I free it without malking it again? Yep. That's crazy. This is the keys. Wait. Oops. Wait, this isn't supposed to go here. This is supposed to be down here. Okay, now we should be good. No, we're not. Fuck. This is the same spot? Oh. I think it's because I'm not using the string function. So we should say sn printf table. Actually, I'm just gonna use string copy to see if it actually works. Oops. What was the problem? Hmm? Oh. This is supposed to be keys. Wait. Oh, okay. Yeah, I did malloc it correctly. I just didn't. $24. $24 and what? Boarding pass example. Why?
You're right, sorry, you're right, though. Yes, yes.
Wait, what the fuck did I do here? Is that the right order? It's the destination. Oh, okay. Interesting. And the size. So that means this needs to be this. Oh, it's in a different spot. What the fuck? 69 in here. It's right of size in a 4-byte region. And we mallocked it at 68. Post one. $54 in hash table. An add element. I feel like that's just a normal segfault. Never mind. It's a read of size 8, and it's a 24-byte region. So it's after. It's an add element. It's not there. It's at removed 26. Yep. So it's, we tried to free. What if we just... I don't want to do that though. It's 86. I forgot already. Can I do this? Is that a thing? Damn. Alright, I'll figure this out later. I gotta take a break. I have some stuff I got to do. Alright, I'll come back to this. But for now, I'm gonna think about it.